I'm Eleni, and I'd like to talk to you about our spotlight paper on designing decision support systems with counterfactual prediction sets. In this paper, we focus on decision support system that assist experts to solve multi-class classification tasks. Typically, such systems consist of a classifier that is trying to directly solve the classification task for the expert by predicting the ground truth label. Then the human expert sees this label and has to decide if they're going to follow the recommendation of the classifier or choose any other label to make their final prediction. The setup brings us naturally to the question, okay, when our expert can know that they can rely on the predictions of the classifier? And to answer to this question, there have been several attempts to try to add some information on the output of the classifier, such as the accuracy, the confidence, or some explanation on the predicted label to help the expert understand when they can rely on the predictions of the classifier. And there have been many empirical studies that try to assess how this information actually help the expert understand when they can rely on the predictions of the classifier. But unfortunately, there was no clear conclusion on how experts could use this information to avoid misplacing their trust in the system, meaning to trusting it when it's incorrect and not trusting when it is actually correct. And this is our main problem here, how we can avoid the risk of misplacing the trust of the expert in the system. And to solve this problem, our goal is to guarantee by design that our decision support system will not require the expert to understand when they can rely on the predictions of the system. And to achieve this goal, we're going to reconsider the basic design of decision support systems that try to directly solve the task for the expert and come up with a system that is trying to simplify the task instead, meaning that instead of giving single label to the expert, our system, we want to give a set of labels, giving a prediction set, and ask the expert to choose from this set. Now, if we have no guarantees that the true label will be in the set, our expert will still need to decide if they're going to choose a label from the set, like to understand if the set includes the true label. Otherwise, the set will mislead the expert. Therefore, we not only want to simplify the task with a prediction set, but want to do this reliably, meaning that we want to guarantee that the true label will be in the prediction set, in which case we cannot mislead the expert. And to achieve simplifying the task reliably for our expert, we're going to use the framework of conformal prediction that comes with a very nice statistical guarantee. Conformal prediction guarantees that the true label will be in the prediction set with probability 1 minus alpha, where alpha is a parameter that we can choose any way we want. And this brings naturally to the question, okay, what alpha values do we choose, right? Well, if we choose alpha 0, we'll have 100% probability that the true label will be in the prediction set, but on the same time, our prediction set will include all possible labels, and in this case, we will completely fail to simplify the task for our expert. Well, if we choose a slightly larger alpha value, we will end up with prediction sets that are smaller, and the prediction task will become easier for our expert. But as we keep increasing the alpha, it will also become likely that the true label is not in the prediction set, in which case we will mislead the expert. Therefore, the alpha value trade-offs how much we simplify the task for our expert and how much we mislead them. And what we want to find is this sweet spot for alpha, the optimal trade-off, under which our human expert achieves the maximum accuracy. And we do this in our paper by using we find the alpha value that maximizes the expert accuracy by using a bandit algorithm together with a counterfactual monotonicity assumption that allow us to significantly speed up our bandit algorithm. To evaluate our method, we conducted a large-scale human subject study where we tried two different implementations of our system. In one implementation, our human participants could choose only from the prediction sets, and in the other implementation, our human participants were shown the prediction set, but they could choose any other label. And the first interesting finding from our study was that for no matter what the alpha value was, the experts choosing from a prediction set achieved higher accuracy than the experts that were allowed to choose from outside the prediction set. The second very interesting finding was that our bandit algorithm using the counterfactual monotonicity assumption did manage to find the alpha value with which our expert achieved the optimal accuracy. And last but not least, the human participants using the optimal alpha value achieved higher accuracy than they would do on their own and higher accuracy than the classifier on its own. If you want to hear more about our methods and study, I'll be delighted to see you in our poster in session 3 in Hall C. Thanks for watching.